right. Hello, everyone. Welcome to this session NET201 on AWS Networking Fundamentals. My name is Anand Gaitonde, and I'm joined by my colleague Rizwan, and both of us will be taking you through this session. So let's take a quick look at the agenda for this session. All right, so this is a 200 level session designed to provide you with fundamental building blocks of networking on the AWS cloud. And we do expect some familiarity with networking concepts like IP routing, DNS, CIDR notation, security, and so on. And the way we will go about this session is we'll talk about some of the components of the physical infrastructure world, and then how that translates into some of the virtual or logical concepts on the AWS platform. We will then build on top of that by talking about different connectivity mechanisms for connecting your networks on AWS and to your on-premises environment. Let's start then by taking a look at the AWS global infrastructure. So the AWS global network comprises of redundant 100 gigabit Ethernet links connecting our infrastructure across 6 continents. We operate this network, so we are able to provide purpose-built, encrypted, highly available, and scalable networking infrastructure for our customers. And so the AWS infrastructure comprises of AWS regions, which are geographical areas around the world, where we have clusters of data centers where you can deploy your applications and resources. Each of these regions are separate from each other, so it provides the greatest level of fault isolation and stability. So if you zoom into the AWS region design, each of these regions comprises of multiple data centers clustered together, what we call availability zones, or AZs for short. And again, each region comprises of multiple availability zones, and each availability zone comprises of one or more discrete data centers, each with its own redundant power, networking, connectivity, housed in separate facilities. Each of those AZs interconnect with each other using redundant, dedicated metro fiber, providing high throughput and low latency networking. And at the same time, each of these AZs are separated by a meaningful distance, in many cases several kilometers in length. So on one hand, you have the capability to provide synchronous replication, and at the same time, because of the physical separation, you are able to get the fault isolation from issues like power outages, floods, tornadoes, and so on. So this particular concept of availability zones becomes very important as it provides you the greatest high level of high availability, scalability, and fault tolerance than would be possible in a single data center. So now you can run your applications which span across availability zones and across your regions to provide that low latency and high availability for your end users across the globe. So customers have always asked us to provide a continuum of cloud services starting from the AWS region into your latency-sensitive edge workloads. And they want to use the same set of services, APIs, and tools. So we came up with offerings like AWS Outposts, AWS Local Zones, and AWS Wavelength. So AWS Local Zones essentially brings services like compute, storage, and databases into large population centers or industry or IT centers where no AWS regions exist today. At the same time, AWS Wavelength provides similar services at telecommunication service provider data centers at the edge of 5G networks. And then AWS Outposts brings those capabilities into your on-premises environments and co-location facilities. So all these service offerings essentially are able to assess the breadth of AWS services from your parent AWS region. So now that we have looked at some of the components of the physical infrastructure, let's see how you can create your own virtual network in the cloud. And we call it the Virtual Private Cloud, or VPC for short. So if you recall, we talked about an AWS region, right? So within an AWS region, you can create your own virtual private cloud, or VPC. Now you can have one or more VPCs in a given region in your AWS account. Then region comprises of availability zones. So now the VPC that you've created spans across those availability zones, and each availability zone is identified with a logical identifier, like you see here, like US East 1A, 1B, and so on. And these are randomly generated. So what is US East 1A in your AWS account could be a US East 1F in my AWS account. Now, many times customers do want to co-locate their resources in the same availability zone across multiple AWS accounts. And that's why we provide what we call AZ ID, which you see here at the bottom. And that allows you to identify which specific AZ your resources are going to be co-located in. So once you have the VPC, you want to segment your networks using the concept of subnets. Again, subnets are bounded by availability zone, and you can have multiple subnets within an availability zone. Then you want to launch your resources within the VPC. So resources could be Elastic Compute Cloud instances, EC2 for short, or it could be containers or databases like RDS or Lambda functions, which is our serverless compute. Let's stick with EC2 for now. So when you launch your EC2 resources, they are connected to the subnet by what we call Elastic Network Interfaces or ENIs. And essentially, you are going to launch your resources within the subnet of a VPC. So let's turn our attention to IP addressing within VPC. So we support both IPv4 and IPv6 addressing. And let's talk about IPv4 first. So you can specify a CIDR block for your VPC, which can range from /16 to /28 in size. And this network is considered to be private by AWS. So we strongly recommend customers to use RFC 1918 for address allocation within the VPC. Now again, once you assign this CIDR block to your VPC, you cannot change it. So you may want to do some upfront address planning. Once you do that, you can then assign CIDR blocks for your subnets. Again, these range from /16 to /28 in size. And once you do that, you can now start allocating that address block to your resources in the VPC. So IP addresses can be assigned to your EC2 resources at launch, or you can manually assign them as well. You can also assign secondary IP addresses to your Elastic Network Interfaces, or you can have multiple ENIs for a given EC2 instance. So let's say if you didn't quite get your addressing plan right. As you see here at the top, you can assign secondary CIDR blocks for your VPC. And now within a subnet, it's important to note that there are 5 reserved IP addresses. So the first 4 and the last one IP address of your CIDR block is reserved. The rest is available for address allocation. And then again, at the VPC base address +2 resides the Route 53 resolver, which provides DNS query resolution for your VPC. So we talked about private IP addresses here. Let's turn our attention to public IP addresses. So again, you can use the public IP address space provided by AWS, or you can bring your own IPv4 in select AWS regions. And you can assign these public IPv4 addresses automatically at resource launch, or you can assign them manually by using what we call elastic IP addresses or EIPs. And the key difference between these is that automatically assigned IP addresses cannot move across resources, whereas elastic IP addresses can be associated or dissociated from an ENI or from a given EC2 instance. All right, so here I have a Linux EC2 instance that is configured with IPv4 addressing, and I'm running a ifconfig command. As you can see, the private IPv4 address is present on the network interface, whereas the public IPv4 address is not seen. And the reason is because the public IPv4 address is a one-to-one netted address at the VPC boundary. So that's why you don't find it on the network interface. But let's say if you want to query the public IPv4 address, you can use what you call the instance metadata service to query the public IP address. Now, instance metadata, as you might already know, is just the configuration data of your EC2 instance. And this instance metadata service is an on-instance component, which allows you to query this configuration data. So your business, your applications or scripts can query this for your business logic. Here I'm just querying the public IPv4 address here. All right, so now let's talk about IPv6 addressing. So within your VPC, we support both dual stack subnets as well as IPv6 only subnets. And the key difference here is for IPv6, the CIDR block cannot be specified, the size of the CIDR block cannot be specified by you. So it is predetermined. So for the VPC, it is /56 in size. And for the subnets, it is /64 in size. And like I said, you can have subnets either at IPv4 subnets or dual stack subnets like the ones at the top here, or IPv6 only subnet, like the one at the bottom shown in this diagram. Then you can assign those resources with IPv6 address automatically at resource launch, or you can assign them manually as well. Just like IPv4, even IPv6 addresses, address block has the first 4 and the last 1 IPv6 address of a subnet is reserved. The rest is available for address allocation. And then again, you have the VPC router address, which is learned via route advertisements and depends upon the virtual MAC address. Now, IPv6 address is a global unicast address, right? So you use the same address to communicate internally within your VPC as well as to the internet. So there is no requirement of a NAT here. And with IPv6, keep in mind that you cannot have secondary CIDR blocks associated. That is not supported. And then elastic IPs for IPv6 is also not supported. And let's say if you are launching an EC2 instance within your subnet, but the IPv4 space is exhausted, then you won't be able to launch it, even though IPv6 address space is available. All right, so here I have a Linux EC2 instance again with an IPv6 stack. And as you can see on this interface, I can see the IPv6 address available. And that's because there is no requirement of a NAT here. And then again, I have the default router address, the link local address available here, which is learned through the route advertisement. Again, for IPv6, you can bring your own IPv6 in select AWS regions, or you can use the ones which AWS automatically assigns. So now that we are on this topic of IP addressing, right? So one of the challenges that network administrators face is to manage this IP space across different networks. And they've been using homegrown tools or spreadsheets to manage that. So that becomes quite cumbersome. They require manual updates and synchronization across different networks. That's where at reInvent of 2021, we came up with a service to help address that challenge, and that is called Amazon VPC IP Address Manager, or IPAM for short, which helps you to plan, allocate, monitor IP usage across AWS environments across regions. And it essentially does 3 things. First, it automates your IP assignment. So basically, for getting your IP blocks, you don't need to cut tickets or have a request approval workflow. Second is it monitor your IP usage. So you can look at how much of your IP space is being utilized. And then you get alerts on whether there is overlapping CIDRs within your network and so on. And then IPAM actually retains the monitoring data for almost 3 years. So you can do historical analysis for audits, for troubleshooting, and so on. And then IPAM as well provides business rules, like you can specify which IP blocks should be used by which AWS accounts or which regions and so on. So what you are able to do is arrange IPs based on the security or routing needs. So you may have a top-level pool which you further subdivide into different regions where your workloads exist. You can further subdivide that into, let's say, dev and prod environments and so on. This works for both IPv4 and IPv6. All right, so now let's turn our attention to, back to our VPC where we had the subnets. So each subnet is associated with a route table. And by default, you have the VPC main route table to which it is associated with. In this VPC main route table, there will be like default route table entries which point to the local CIDRs of the VPC for both IPv4 and IPv6. Now you have the option to create custom routing tables as well, and then you can associate your subnets to that route table. But again, keep in mind that your subnet will be associated with a single route table at any point in time, but a given route table can have multiple subnet associations. Now, when we want to send traffic from the EC2 instance in one subnet to another EC2 instance in another subnet, it will refer to this route table and determine what is the next hop. So in this case, it is the local CIDR, so the next hop will be local. So it will send it to the VPC router, which then forwards it to the eventual destination. So now, when you say the VPC router, it's not a single physical device, but it's just the VPC software which takes care of the packet forwarding. Now you also have the option, as you can see on the top route table, of having a specific route to a specific ENI and so on, and that lends itself to several networking use cases. One of them could be if you want to do traffic filtering between subnets, right? All right, so at the instance level, there are three main services which you want to be aware of. That is the first one is the EC2 Instance Metadata Service, or IMDS, which I was mentioning earlier. And that, again, allows you to introspect the instance metadata. Here, again, I have an example where I'm querying the host name of the instance, right? And this is available at the 169.254 address. There is an IPv6 address for that service as well. One interesting example is you use AWS IAM to provide roles to your EC2 instances. Let's say to access an S3 bucket, and the corresponding temporary rotating credentials are maintained by the IMDS service so that your applications can query that. The second service is the Amazon TimeSync service, which provides an NTP endpoint to a fleet of satellite-connected atomic reference clocks in your AWS region, and it helps you to smooth any leap seconds added to the UTC time. And then the third is the Amazon Route 53 Resolver service at this 169.253 address. And again, there is an IPv6 address for that service. This is used for your DNS query resolution within the VPC. And I have an example here using the IPv6 service to query the domain name of a particular DNS name. All right, now let's talk about the security within the VPC, right? And I will have an icon on this slide and subsequent slides, which just means that there is security content on this slide, so you may want to just pay a close attention to that. Now, the security of a VPC can be thought of at three levels. One is at the instance or the interface boundary. The second is at the subnet boundary. And the third is at the VPC boundary. So let's tackle them one at a time. All right, so security groups are stateful firewalls that you put around your EC2 instances. Well, actually, you put them around your ENIs, but let's stick with EC2 instances for simplicity. Now, by default, inbound security group rules deny all traffic, right? So your EC2 instance is isolated from the traffic at all. But let's say if you want to allow SSH into your EC2 instance, then you can put an inbound security group rule, which allows traffic over TCP port 22, and that will ensure that traffic coming inbound into your EC2 instance is allowed. Now, since security groups are stateful, even the outbound traffic is allowed as well. Now, security groups also have outbound rules, which is for instance-initiated traffic outbound. And by default, all traffic is allowed by those outbound rules. Now, let's say if you want your EC2 instance to talk to a specific destination, you can put a specific rule specifying that destination as you can see here. And that will ensure that traffic going outbound to that destination is allowed. And then again, by virtue of it being stateful, the return traffic is allowed as well. So this becomes useful for the security of your EC2 instances. And let's take an example of how you can assign it to multiple EC2 instances, right? So let's talk about EC2 auto-scaling. So when a scale-out event occurs and as new instances get added, they automatically get added to this security group. So you don't need to do any additional configuration. And you get a consistent network security parameter for your fleet of instances. Now again, keep in mind, we had this rule for allowing SSH access. So you will be able to do SSH between these EC2 instances, but you will not be able to do any other traffic, say ICMP ping, for example. And so how do we enable that, right? So essentially, security groups, within the security groups, you can have source for inbound rules or destination for outbound rules using IP addresses, like the way I shown here in some of the examples. Or you can specify groups of IP addresses using an abstraction called prefix list. Or you can reference security groups itself. So each security group has an identifier, like a security group ID, as you see here at the bottom. And you can use that within your security group rule. So here I'm referencing the same security group and specifying that all traffic is allowed. So this now will ensure that all traffic within your EC2 instances can flow in. All right. So I also mentioned one thing about prefix lists, right? So that becomes a very important tool in your hands, because let's say if you are having complex networks with a lot of CIDR blocks that you have to manage, then you have the capability to group those CIDR blocks into what you call a prefix list, and then use the prefix list as a reference into your security group rules. And that really simplifies the management of your security group rules. All right, so this aspect of referencing the security group within itself becomes an important tool for managing the security of your VPC. So let's take an example here of a web application, right, which wants to receive traffic over HTTPS over TCP port 443 from external sources. So you put an inbound security group rule which says allow traffic from all sources over TCP port 443. And that ensures that that traffic flows through. Now the web server also wants to talk to a backend database server. It could be an RDS Aurora database receiving traffic on TCP port 3306. And so we put a security group around our DB instance, and that will have a rule allowing traffic on your TCP port 3306. But as you can see here, I'm specifying the source as the web tier security group by referencing that particular security group. So that will ensure traffic comes from the web server into your databases, but it does not allow any other sources to send traffic to your database, and ensures the security of your data layer. All right, so one other aspect I wanted to show here was, let's say if your web servers had to talk to multiple applications which are in different networks, right? And those have different CIDR blocks. And so if you were to do that and put some outbound security group rules, this is how it would look like, where you put in, let's say, those outbound security group rules for HTTP and HTTPS traffic to those different networks. Now here is where the prefix list comes in handy. You can combine all those CIDRs of your networks into a single prefix list, and then reference that in your security group rule. And as you can see, it just simplifies your security group management. Now this really becomes useful because you can centrally manage your prefix list and then share it across your AWS accounts, so that it can be used in security groups or routing tables and so on. And so this becomes useful, especially when, let's say, you add an additional network and an additional CIDR block. You just have to update the prefix list, and all your security group rules will automatically get that update. All right, so now, when this web tier starts scaling out, right, like as we get more instances added, without any additional configuration needed, they will still continue to receive traffic from those external clients. And then at the same time, it will also be able to talk to the database instances. In the same way, as additional database nodes get added, they will continue to receive traffic from the, from the web tier. All right, now let's turn our attention to the subnet boundary. And at the subnet layer, we have network access control lists which wrap around our subnets, and they provide stateless packet filtering. So which means you need to have rules for both the directions of the traffic flow. So by default, you have the inbound NACLs and the outbound NACLs which are present, which allow that traffic flow to happen. So in our previous SSH example, essentially when we sent traffic to our EC2 instance, that was allowed by the inbound rule. And then there was outbound rule which ensured that the reverse traffic flow also worked, and that's how the connection setup succeeded. Now, let's say if you remove the allow statements from the outbound rules, what would happen is the incoming traffic would still come to your EC2 instance, but the outbound traffic flow will not work, and the connection setup will fail. So now you also have the option to specify specific sources and destinations within NACLs. But of course, in this case, you can just specify using IP addresses. So in this case, again, I'm wanting to allow SSH only from a specific source. So I have an inbound NACL rule which specifies that particular source IP address. And then I also have the outbound rule which allows the reverse direction of the traffic flow. But again, here, I specify the ephemeral port range because clients will be using one of the ports from the ephemeral port range to communicate with the EC2 instance. So now, one of the best practices for using NACLs is, you don't want to be specifying very detailed rules with each IP address specified in the NACLs, because you can quickly exhaust the limit of the NACLs that is possible. So normally we would encourage customers to use like broad level of protection. So let's say if you want to, not have any telnet traffic in your environment, right, over port 21, or you do not want any HTTP over port 80 coming into your environment. So NACLs can be best used for putting those protections in place, and then security groups for more specific security needs. All right, now let's turn our attention to the VPC boundary. So here in this example, I have my web server and the database server on the left, and I have my bastion server and the observability server on the right. And what I'm trying to do is SSH into this server. When I try to do that, the VPC, it never crosses the VPC boundary. Well, why is that? So essentially, there are 5 things that needs to be happen for traffic from the internet to come into our VPC resources. So first is it should have a public IP address. Then the second is it needs to have an inbound security group rule, as you see here for the SSH access. We have that as well. Next is at the subnet level, we need to have the NACL rules. So we have the inbound NACL rule, which allows that traffic, and then we have the corresponding outbound NACL rule as well. Now, apart from that, we need an internet gateway. We didn't have that in our architecture, so let's add it at the VPC boundary. Now, internet gateway is that component which acts as a bridge between the traffic, between the internet and your VPC resources. And it is also that entity which actually provides that one-to-one NAT between your public IPv4 address and the private IPv4 address of your resource. Now, once you have that, you can create a routing table entry which specifies that for all external destinations, the next hop is internet gateway. And with all these in place, now you will be able to SSH into your bastion server and access the observability data. So with that, we've looked at the various VPC constructs, and now there are other capabilities of interconnecting, having multiple VPCs within your network and interconnecting them, and then interconnecting those to your on-premises networks as well. And I'll hand it over to Rizwan to talk about some of those capabilities.
Thank you, Anand. Routing as well as your connectivity inside your VPC, and now we're going to look at how you can extend that connectivity out to the rest of the world. So as you can see, we have a bunch of different constructs here, gateways, various names that you see on the screen here, and each one of them has a different purpose, and we'll talk through them as to where and how you can actually use them and how they actually help connecting to the outside world. So we'll start off with the 2 of them, the Internet Gateway and the NAT Gateway, and as Anand mentioned in his section about how you can actually use, address your VPC both from an IPv4 and IPv6 perspective. So let's say in this example, you have a VPC which has both IPv4 and IPv6 addresses. It has two public subnets, 2 private subnets, and resources in both, and you want your resource to be able to talk to the internet. How would you do that? First thing is you have to have an internet gateway, as we talked about earlier. The public resource has a public IP address. In this case, it's an elastic IP address that you have assigned to the resource. And then the next step is where you would actually set up your subnet route table and point your route to the internet gateway so that the resource in this case would be able to talk to the outside world. And as you can see, there's a default route out 00/0 that points to the internet gateway. And similarly, there's a : /0 corresponding for IPv6. And now your resources are able to then talk to the internet. How about the private subnets? The resources which are in the private subnets, which have private IP addresses, how they are able to talk. For that, we have another service called NAT Gateway. The NAT Gateway is a managed service that allows your private resources to be able to talk outside. It does one-to-one natting. You deploy it in your public subnet with a public IP address or elastic IP, and you update your route table similarly as to how we saw for the public subnet, where you have a default route out to the internet gateway. So that takes care of the subnet where your NAT gateway lives, but what about your private subnet? Because that's what you are trying to actually connect to. So in your private subnet, which has a private IP address, you would again have a default route, and in this case, your default route actually points to the NAT gateway, and then your resource is able to then, via the NAT gateway, talk out to the internet. So this is all well and good for IPv4. What about IPv6? So as Anand mentioned in his section, IPv6 addresses are globally unicast. So within our VPC, even though they are globally unicast, that doesn't mean that your resources are able to talk outside, and outside resources can talk to those IPv6 addresses. So for that, we have another gateway called an egress-only internet gateway, similar to internet gateway, but it is primarily meant for IPv6 resources. So in this bottom left, you see a private resource, private subnet with an IPv6 address that you want to be able to talk to the outside world. You create an egress-only internet gateway, attach it to your VPC, and then again, update your subnet route table. In this case, you have ::/0 pointing to the internet EIGW for short, and your resource is now able to talk outside using the egress-only internet gateway. And just like with IPv4, your outside resources cannot initiate connections to the private, or in this case, the IPv6 resource. So just combining them together, so you can have both for IPv4 and IPv6, constructs available: internet gateway for IPv4 and egress-only internet gateway for IPv6 resources. Moving on, we have some other methods to now be able to, this is how you would actually connect using public connectivity, but how do you actually do it for private? So we have other methods. One of the most common sort of use case where you say, okay, I have resources, but I don't want them to be able to talk to each other using internet gateways or public IP addresses. I want total private connectivity. So how would we be able to do that? So for that, we have a construct called VPC peering. So what VPC peering allows you to do is to establish private connectivity using private IP addresses between your VPCs and resources. And the resources inside your VPC are able to talk to each other as if they were in the same network. So in this example, we have two VPCs with both IPv4 and IPv6 addresses. And you can actually VPC peer within the same account. You can VPC peer across accounts. You can even peer across regions. So in this case, two VPCs with IPv4 and IPv6 addresses, and you set up a peering connection. So peering connection is basically a mechanism where the source, you define what is your source, what is your destination VPC, and there has to have a handshake that happens, meaning the requester initiates the request, the responder accepts it to say, yes, I want to accept this peering connection, and then the peering connection establishes. After that, you also have to set up your subnet route table, just like we did for the internet gateway and the other connectivity, where you point your route to the other side so that the resources in your private subnets are able to know how to reach the other side. So in this case, you see 10.2/0016 points to the peering connection. Similarly, on the right-hand side route table, you point to the peering connection so that the resource would know how to reach the other side in the VPC. So one thing to note is that for VPC peering, you have to have non-overlapping IP CIDR blocks for your VPC, and that are evident, as you can see, in the CIDR blocks for your VPC. That's a requirement. Even for dual stack VPCs, where you may have IPv4 and IPv6 addresses, you still have to have, even if your IPv6 addresses are non-overlapping, your IPv4 addresses would also need to be non-overlapping. That's a hard requirement. You can actually also extend VPC peering to not just two VPCs, but to multiple VPCs in a region, right? So here we have a bunch of VPCs. And you can actually create a full mesh network of peering among together so that they all can talk to each other, right? All you have to do is, again, set up the peering connections between those VPCs, set up the route tables, and provided that your security groups are not blocking anything, those resources can privately talk to each of these VPCs among themselves. One thing to understand or note is that VPC peering does not allow transitive routing. So what does transitive routing mean? So transitive routing in this case means that, let's say you have VPC 1 and 2 peer together and 2 and 3 peer together. VPC 1 and 3 cannot talk to each other just because they have via the VPC 2. Right? So in order for the resources to be able to talk to each other, they have to be connected directly via the peering connection. So this is all well and good if you maybe have a few handful of VPCs, but what if you have tens of VPCs, hundreds of VPCs in a region, across the region that you want to build your global network? VPC peering from an operational perspective can be a little bit of a overhead to maintain, manage all these full mesh peering connections. So how do we actually solve this problem? So a couple of years ago, we released a new service called AWS Transit Gateway. AWS Transit Gateway is a virtual distributed layer 3 cloud router that scales to thousands of VPCs within a region. You basically create a AWS Transit Gateway, and then you basically attach your VPCs that you want to be able to communicate to the transit gateway using a construct called attachments. And attachments basically creates elastic network interfaces within the VPCs, the target VPCs, the subnets inside those VPCs, so that the transit gateway is able to then communicate to those VPCs. So you create the attachment to the VPC in question. You associate that attachment to the transit gateway. In this case, it actually shows you how you can actually create your transit gateway. Basically, you select your subnets where you want the ENI to exist for transit gateway, and then you give it a name, and that's the minimum that you would need. By default, the DNS support and IPv6 support is enabled. Transit Gateway also, since it acts as a distributed layer 3 cloud router, virtual cloud router, it has its own route tables, just like your VPC route tables. And you can have more than one route table within the Transit Gateway. And once you define your route table, Transit Gateway also can help segment your traffic. So what it means in this example is, let's say in these 5 VPCs, you have VPC 1 is attached to the transit gateway. Let's call it attachment 1, and subsequently for VPC 3, we are attachment 3. You set up your transit gateway route table so that it actually knows where to send the packet to when it actually receives it from the VPC in question. So in this case, VPC 1 and VPC 3 are attached to the same route table within the transit gateway. Similarly, VPC 4 and 5 with their corresponding attachments are in a separate route table, call it route table 1 and route table 2 respectively. So now VPC 4 and 5 can talk to each other because they are in the same route table. However, VPC 4 and 1 cannot talk because they are not in the same route table. So if VPC 4 were able to send anything destined for VPC 1, there is no route and the packet will get dropped. So that actually allows you to create segmentation within your network using transit gateway route table and gives you the capability to segment your traffic. How do you actually extend it to the multi-region? So this was for single region. If you were to do it for multiple regions, as your global footprint grows, you can actually take and peer them together. So here we have, in this example, 4 regions. And Transit Gateway is a regional construct. It does not live inside your VPC. It lives within the AWS region. So you have 4 regions with 4 multiple VPCs within each region. And you have Transit Gateway in each region that you have created, and they are connected or attached to those respective VPCs within the region. In order for those regions to be able to talk to each other, you can actually peer these transit gateways together. So just like we looked at and talked about VPC peering, similar construct where you can set up these peering attachments between these transit gateways and to set up a full mesh network. And key thing to note is that all the traffic even for VPC peering as well as for transit gateway, these peering attachments, they all remain on AWS backbone and is also encrypted. So this is all well and good. You still have to set up the route tables for your transit gateway route table. You have to set up the VPC peering attachments, and you have to maintain it. As we add more regions, this can again, as we saw with VPC peering, can create some operational sort of like tasks to be able to manage and add or remove. What if there may be an easier way to basically build this global multi-region network? So last year at reInvent, we announced a new service called AWS Cloud WAN. And AWS Cloud WAN solves this problem by setting up the this global network in minutes. It allows you to create these segments. So we talked about the transit gateway route table and the segmentation that you can achieve within your VPC within the region. And Cloud WAN actually allows you to extend it globally. So let's say you have, in this example, 3 segments. You have prod, dev, QA, or in this case, shared services, engineering, and sales. And you want the VPCs that belong to that particular segment to be able to talk to other VPCs in other regions seamlessly. And Cloud WAN actually allows you to do that. It creates this full mesh network on your behalf, connecting all these regions together. If you may be on-prem with any kind of hybrid or edge connectivity, it also helps solve your edge connectivity. So let's say you may have AWS site-to-site VPNs. You may have some SD-WAN via the Transit Gateway Connect also set up. You can also integrate that into your Cloud WAN fabric and build this global connectivity. And all of this is actually controlled via a central automation policy. So you don't have to write manual update route tables or things that we talked about earlier, change subnets and whatnot. You define a central policy, which is fully automated, and you push that policy based on your requirements, and it gets deployed underneath by the service and in the regions that you actually select. It also gives you centralized monitoring and visibility using Network Manager. It is available in public preview right now, so there is no need to basically whitelist or anything like that. If you are interested, I would encourage to go in and check it out. Okay, so how do we now access other AWS services? So we talked about the global connectivity, single region, multi-region. There may be common use cases where you have resources running within your VPC that needs to go and talk to other AWS services that live inside the region. So this is just a sample example of a few here. So as we saw earlier, you have a VPC with both IPv4 and IPv6 addressing. What would you do? You would create an internet gateway for your public subnet. For your private subnet, you would create a NAT gateway, assign a elastic IP, and then your resource which lives inside your private subnet has a private IP address, is able to talk to the AWS service in question using the internet gateway. So this is all well and good, may solve your problem for such use case. However, there may be use cases where you may require private connectivity, just like we talked about connecting to the outside world using internet gateways, and we then talked about how VPC peering and transit gateways actually help solve those problems. If your use case requires private connectivity to say, okay, I want to talk to S3, I want to talk to Dynamo or many other services privately, but I don't want to use public IP addressing, internet gateway or anything like that, how do we actually do that? For that, again, in this example, we have a VPC with both a public and private subnet. We have a bunch of AWS services as an example, and you want to be able to talk to them privately. So we have a service called AWS PrivateLink, and what PrivateLink actually allows you to do is to be able to privately talk to the AWS services. We have over 170 services right now that actually, and growing, that support AWS PrivateLink. And what the service actually allows you to do is, based on whatever the service that you would want to connect to, you create what you call an interface endpoint. An interface endpoint basically creates an elastic network interface within your VPC subnet. It automatically assigns a private IP address from that subnet range. And then when your resource needs to talk to that service, it would access that VPC interface endpoint, and using PrivateLink as the underlying transport, we take care of all the heavy lifting, and your resources can privately talk to the services in question here. Similarly, there's another type of endpoint. These are only available for two services for Amazon S3 and Amazon DynamoDB. These are called gateway endpoints. And gateway endpoints are slightly different than interface endpoints in a sense that these represent as route table targets within your VPC, not as elastic network interfaces like we saw for interface endpoints. So when you create a gateway endpoint, it creates a prefix list that represents the CIDR block for that service, S3 or Dynamo, as a target for your subnet route table, and the resources are then able to talk to either one of them using the gateway endpoint. Now, one of the best practice for deciding when to use interface endpoint and when to use gateway endpoint is that for any resource within the VPC that needs to talk to S3 or Dynamo, gateway endpoints. For other services, interface endpoints, and especially for S3, there may be a use case or a hybrid use case where you may have something on-prem that you would want to be able to talk to privately and don't want to use S3 public endpoints. S3, Amazon S3 also supports interface endpoints that are accessible over your VPN and Direct Connect that you can actually use to access. So in those use cases, interface endpoints come in handy. You can also apply endpoint policies. So what endpoint policies actually allow you to do, these are not a replacement for your IAM policies or any of your existing IAM policies. It's in addition to those, and it actually allows, gives you more control over who can actually access that service using the interface endpoint. So in this case, this is just a sample that says, okay, this particular role is allowed to access this endpoint. So you can control and tie it down further. Okay, only such and such role, such and such user is able to access this service using the endpoint, everything else will be denied. You can extend PrivateLink not just for AWS services. What if you have an application that you want to expose to other users within your own organization, within your VPC, or to other consumers who may be on AWS already? So PrivateLink also helps solve this problem by allowing you to do the same thing. How would that work? So let's say we have two VPCs. We have a consumer VPC and a service provider VPC. So provider VPC is your application that you want to be able to expose for others to consume, which lives inside your service provider VPC. You create a network load balancer. Network load balancer is our layer 4 load balancer from the load balancing family. You deploy your application just like as you would do behind a load balancer, in this case, network load balancer, within the target groups. And then you actually create an endpoint service that creates interface endpoints within the other accounts, consumer VPC on the other account. And on the consumer VPC side, they would create the endpoint for the service based on the service name that is generated by the PrivateLink service, in this case, the endpoint service. And then just like we saw for interface endpoints, it creates an ENI within the subnet with a private IP address in your consumer VPC, and your application within the consumer VPC is able to talk to the application in the service provider VPC using PrivateLink. Another advantage of PrivateLink is that it allows you to, even if your VPCs on both ends may have same CIDR block, which may be common, both sides could be using same 10.x, for example, CIDR block. PrivateLink handles that for you, and you don't have to worry about natting or any other of that type of constructs to be able to solve that problem. So now let's move on to some of the other constructs here, especially on the private connectivity side. So first one is on the hybrid connectivity, where let's say you have a requirement from your on-prem where you would want to connect into AWS, but you don't want to use public connectivity or anything like that. You want private, dedicated connection into AWS. We offer AWS Direct Connect, and AWS Direct Connect allows you to privately connect using physical fiber cable, fiber connectivity via many of our partners as well as our direct connect locations that are available globally. You pick a location that you want to, that is closest to your data center, wherever that might be. And then you can either select your bandwidth as low as 50 meg to as high as 100 gig, and you can select the connectivity method, whether you want to, if you may be present in the same co-location, you can actually order this physical connection yourself, or you can go through many of our AWS Direct Connect partners. Once the physical connection is set up, you set up your logical interfaces on top of it, which are virtual interfaces. And they actually allow you to actually then privately access any service, any resource that is that may be running inside your VPC, or any of our public service, for example, S3 in this case, Dynamo, and many others that we saw earlier over the same connection. So when you actually set up the direct connect, you can set up either using a virtual private gateway, which is our terminating endpoint on the AWS side. And you also, if you want to go multi-region, which is very common, you can set up a direct connect gateway, which is again a virtual construct that allows you to connect globally to multiple regions over the same physical direct connect connection. So you don't have to have multiple connections in order to build that network. So in this case, you set up your virtual interfaces with direct connect gateway, you attach your virtual private gateway to the direct connect gateway, which then is attached to your VPC, and your resources can then talk to your on-prem network. Similarly, you can, if you want to scale, just like we saw for transit gateway, if you want to scale for hundreds or thousands of VPCs, as we saw earlier, you can use a transit gateway. The construct does not actually change, the method does not change. Instead of a virtual private gateway, you set up a transit gateway, attach it to your VPCs in question, and then you set up your virtual interfaces after you have set up your physical connectivity, set up your direct connect gateway, attach to your transit gateway, and then establish your connectivity using BGP. Optionally, if you may have a requirement or a compliance requirement to connect to or have encryption, you can also order or get MACsec encryption, which is native layer 2 encryption over this physical connection, which is available in select locations, direct connect locations for 10 and 100 gig dedicated connections. Okay, these days, a lot of people are actually working remotely. One of the construct that actually allows you to actually connect privately from your on-prem to your AWS is site-to-site VPN. This is a standard IPsec VPN. So for example, if you don't want to go with direct connect, you don't have that requirement for dedicated bandwidth or connectivity, you just need a encrypted private connection. You can set up a IPsec connection, create a virtual private gateway, just like we saw earlier, attach it to your VPC, set up a site-to-site VPN. Your other end could be a physical router, it could be a virtual router. You can have static routing, you can have dynamic routing set up. We support both based on BGP. Dynamic is BGP based. And your IPsec tunnel is set up attached to your virtual private gateway. It's a managed service, so you don't have to do any kind of heavy lifting in order to address high availability because virtual private gateway gives you 2 tunnels on a single connection, and that is for high availability, so that if one tunnel goes down, it will automatically fail over to the second tunnel. You can also scale your IPsec VPN using transit gateways, and again, transit gateway within the region. In this case, you have 2 VPCs. You can have many more, and then you just set up your IPsec VPNs. But instead of terminating on your virtual private gateway, you would terminate on a transit gateway. And transit gateway, not only from a scaling perspective, also allows you to horizontally scale your VPN because it supports ECMP or equal cost multipath routing. So that means you can have multiple VPNs and you can aggregate your bandwidth accordingly because each VPN tunnel only is limited to 1.25 gig throughput. So that's why if you have a need to scale your VPNs, you can use transit gateway to do so. For remote connectivity, we also have AWS client VPN. Nowadays, many people actually work remotely, and they would need to access their resources or privately over the VPN connection. And basically, the client VPN gives you a fully managed open VPN compatible TLS connection based service that allows you to establish a TLS connection to your VPN, to your AWS resource from wherever you might be. Your client could be mobile, it could be desktop, etc. It also supports split tunneling so that only the traffic that is destined for your AWS resources are sent over this connection, and rest of the traffic will follow your normal internet path. So saves you on data transfer, saves you on not sending everything that's not destined for AWS. It also supports authentication using both Active Directory as well as certificate-based authentication, also using third-party SAML SSO, things like Okta. So if you are using one of those SAML-based authentication, it seamlessly integrates into that. Okay, bringing it all together. So we talked about within the VPC, we started there, connecting out to the internet, how you actually do with the NAT gateway, with the internet gateway. We talked about egress-only internet gateway for IPv6. We talked about VPC peering for private connectivity between your resources. We talked about transit gateway that allows you to scale to thousands of VPCs within the region, also build global connectivity as well, and also how to actually get private dedicated connectivity if you may have a use case, for example, with Direct Connect and also site-to-site VPN. So let's talk about DNS for a second. So Anand mentioned in his section about the VPC DNS. So the Route 53 resolver is our native DNS resolver that provides DNS resolution capability within the VPC. It is available on the VPC +2 address, also the 169.254, as well as the IPv6. And in this case, for example, you have a 10.0.0/16 IPv4 address. So your native DNS resolver would be on the .2, as you can see in this example below. It also allows you to give or resolve DNS host names. So when you launch EC2 instance, you can actually, if you enable the DNS, it will get a private DNS name and optionally a public DNS name as well as a resource-based DNS name for IPv6. And as you can see in the screenshot here below, by default, it is enabled for the default VPC, but you can actually enable it when you create your VPC with DNS host names enabled and DNS resolution enabled, telling that you would want to use Route 53 resolver to resolve your queries. Route 53 also allows you to do public and private DNS resolution. So private DNS resolution is done using private hosted zones, and private hosted zones is basically just a container that contains information that tells Route 53 how to resolve your DNS queries for your domains and subdomains in one or more VPCs that you have created. So in this case, I have a private hosted zone called example.aws that is attached to this VPC. So in this example, I have an application instance on the left-hand side and that needs to talk to a database instance on the right-hand side. They are in different VPC, but they are peered together. So we already talked about how the peering actually works. But then the application needs to know how to resolve it. So in this case, I have a private hosted zone, an A record created for IPv4, db.example.com that resolves to the 10.0.0/1, which is the IP of the database instance, and similarly for IPv6, the quad A record here. So it will actually send the query. It goes to the Route 53 resolver, which lives on .2. In this case, for IPv4, Route 53 will send the answer back. And your application over the peering connection is able to talk to the database instance. So what about the hybrid connectivity? So you may have resources on-prem that needs to talk to do DNS resolution. For that, we actually provide resolver endpoints, and resolver endpoints are basically two types: outbound and inbound. Whereas if you want to resolve your queries for the DNS server that lives on your on-prem, you create an outbound resolver endpoint, which again creates an elastic network interface within your VPC subnet, assigns a private IP address, and then anytime when your resource needs to do the resolution on-prem, you would create a forwarding rule that tells the resource or the resolver saying that if the query actually comes in for this particular domain name, send it via the outbound rule to the DNS server that lives on-prem. Similarly, for inbound, you would create an inbound resolver endpoint, and then the resources on-prem would be able to talk to, do the DNS resolution on-prem, or DNS resolution using Route 53 using the DNS resolver. Let's quickly take a look at traffic visibility options and use cases. The two common ones are VPC traffic mirroring and flow logs. Traffic mirroring is basically doing packet capture within your VPC. You're actually capturing the actual payload of the traffic. VPC flow logs, on the other hand, only captures metadata. So it's not the actual payload, but the actual metadata. And the use cases are slightly different, where your flow logs are important for content inspection, overly permissive security groups. If you are troubleshooting, you want to create some headers, etc. That's where flow log actually comes in handy. Traffic mirroring, as the name implies, is actual native packet payload capturing. Flow logs, this is just a sample where once you actually enable, it captures a lot of these information like source IP, destination IP, and a bunch of other other metadata. You can enable it on a per interface, per subnet, or for the whole VPC. You can send the data to CloudWatch logs. You can send it to Amazon S3, and then use any native capabilities like Amazon Athena to run SQL queries to crunch the numbers. Traffic mirroring, on the other hand, you define a source, you define a destination, and you define whether you want to capture inbound or outbound or both. And then you set up your traffic filters, which tells what kind of traffic that you want to actually capture. And then you create a traffic mirroring session that ties these three together using the filter, and then you can use either your native capabilities on your VPC, like open source tools like Suricata or Zeek. You can use that for any kind of traffic analyzer. You can use a lot of our partner offerings available in marketplace to do the analysis as well. Lastly, for infrastructure monitoring, we have the native CloudWatch service that gives you the capability for both capturing metrics. By default, it collects supports more than 70 different AWS services, and also allows you to create alarms based on the thresholds that you may be interested in, and send out notifications once those thresholds get breached. In this example, when we talked about Direct Connect, this is just a sample dashboard that shows you that you can actually build these dashboards using key metrics, things like packet in, packet out, connection details, and many others, depending on the service that you may be interested in. And it gives you a quite detailed visibility into your metrics. You can also then create alarms based on the thresholds that you actually set up that would trigger notifications. You can do automations like Lambda-based, send out SNS notifications, and also use CloudWatch anomaly detection, which applies machine learning to the CloudWatch data, and basically call out any outliers that maybe it may actually detect. In this case, all of a sudden the traffic drops based on the baseline that it actually sees, indicating that there could be an issue. So we talked about a lot of those things. We have over 500 plus free digital courses and learning paths for you to take advantage of. We also have a lot of certifications that you can actually, if interested, can take a look at. If interested, you can scan the QR code to get more information. And with that, thank you for your time and for your attention.